I'll begin in a few minutes. If my voice sounds like I just wake up, because I am. Hi, Vernon. Hi. Well, I'll begin in a few minutes. Actually, let me just close my own stream. Yeah. Hi. Hi. Hi, guys. Yeah, for some reason, I couldn't sleep very well last night. As you guys, if you are in the Discord server, then you probably know. I was still replying to messages around 3 a.m., if not later. So, yeah, I had like 2 hours sleep last night. And after the live stream, I need to go to church in the afternoon. And also in the evening, I have other church duties. So, big day. Yeah, all right, guys, um, let's get started. Shall we? So, today, this is a plan. We're going to finish the discussion on sufficient statistics. I joined midway in the series. I haven't read this book yet. Wonder how long I need to catch up. Actually, yeah, Vernon, I'll give you a brief recap of what we did. So what we are trying to do today is to finish the topic of sufficient statistics and do some exercises. Okay, we haven't done much exercise in this book, but we can make that up today. Here, this is the mathematical statistics part, and in the ballistic part of the stream, we're going to recast some of the results we seen last time on rigid body motion and recast them into the language of linear algebra and vector analysis. Okay, so last time we seen because or what let's just remind ourselves what we're trying to do overall, like in the long term, what we want to do in the ballistic part of the stream down the road is we would like to analyze precession. If you look at the thumbnail, you see a spinning shell, a shell along its trajectory, right? It's a typical trajectory for projectiles, and to analyze the precession, you need rigid body mechanics. And here we're in the very basic part of the rigid body mechanics, and we'll see how the modern artillery system analyze the precession of the shell. Hopefully, we can cover both analytic solution and numerical solution. It's a very cutting edge technology. I mean, it's not that cutting edge; it's with Cold War like technology, but it's still considered the most advanced artillery system. I mean, not artillery system, but artillery modeling today. All right, so coming back to the notion of sufficient statistics. So, what is sufficient statistics? Well, before we look at the definition, let's just recall a few examples. Okay, actually, just one example would suffice. So, if we look at the normal the normal distribution as a model, the normal called the location normal model. Hello, Wendelin. The location normal model, basically you have the unknown mean, and the variance is known. So what ended up happening is if you calculate the likelihood function and do some simplification, okay, I'm just going to I'm not going to rederive everything because we did that a few streams ago. The likelihood function, okay, has this form. Actually has this form. has this form, and as you can see, which part we can tell which part really depends on theta. Okay, because likelihood function at the end of the day is a function of theta. X1 all the way to xn, these are data points that are considered given, right? That's the fundamental difference between likelihood function and the joint probability function. Joint probability function, even though numerically have the same value, its perspective is completely different. In joint probability density function, theta is fixed, and x1 all the way to xn are variables. And here, we're seeing x1 all the way to xn as fixed. So here's what happens. The first factor has only to do with sigma naught square, which is constant. Okay, that's considered given. So nothing interesting here. The second term we see it has theta. So this part is important, right? So we need the dependency on theta, and this is exactly where the dependency on theta occurs. And lastly, we have the final term, exponential time minus m minus 1 over 2 sigma squared times s squared, where s squared is the sample variance. So in the last exponential term, we see that, last exponential factor, we see that theta is not here. Theta not here. So as far as this likelihood function is concerned, what only matters is the middle factor. Remember, we said likelihood function is not unique. Likelihood function is simply a ranking system on the parameter space. It's simply a ranking. Only its relative values matter. So the first factor and the final factor can be absorbed into a multiplicative constant. So therefore, we say an equivalent, a simpler version of the likelihood function is then just given by the middle exponential factor. And now you can see the likelihood function is parameterized by the sample, of course. It's a function with an argument theta, and it's parameterized by the sample x1 all the way to xn. But the sample, its dependency through the sample is only through x bar. That is to say, if you have two samples with the same x bar, the likelihood functions are the same. Or should we be more carefully and say the likelihood functions are equivalent. If you have two sample with same sample mean, the likelihood function would be the same. And that's exactly what motivates the definition of the sufficient statistic. Here we go. A function t on the sample space is called a sufficient statistic for the model if whenever their values are the same, t of s1 equals t of s2, then the likelihood function specified by s1 is equivalent to the likelihood function specified by s2. You see, here L dot given s1 is c of s1 s2 times L dot of s2. So L given s1 is simply a multiple of L of s2. Right? The multiplicative constant can depend on the sample points s1, s2, but it does not depend on theta. So basically, this statement basically says the two likelihood functions are equivalent. Whenever t of s1 equals t of s2, then s1 and s2 gives us equivalent likelihood functions. Therefore, it's called sufficient statistics. Knowing the value of t is enough to determine the likelihood function. Okay, so yeah, that's pretty much all we need. So Vernon, you wonder how long you need to catch up. Of course, it depends on your background in probability and statistics, but basically, this is all we need for today. And this is all we need for today. So that's the sufficient statistic notion. And of course, this is one of the equivalent ways to find equivalence, to define or to characterize sufficient statistics. Here we have a theorem. It's called a factorization theorem. Now this is quite useful. That help us identify sufficient statistics. Okay. Here in the statement, here in the statement, it appears to give only a sufficient condition for being a sufficient statistic. I know this is confusing, but yeah, this is if blah blah, if such and such, then T is a sufficient statistic, right? So that's this theorem, but actually the converse is true as well. We proved it last time with the help of Casella and Berger. So basically, the converse is also true. So if T is a sufficient statistics, then the premise is also true. So here it says if the density for the model factors, actually this is just the density for the sample. Okay, f theta of s, or you can simply regard this as a likelihood function. Same mathematically, this is the same. Okay, mathematically the same values, and it can be factorized into this form. H of s, this is a function that has only to do with s, not theta, and g theta of ts. So g theta of ts depends on both theta and s, but it depends on s only through t. So if you have this factorization form, then T is sufficient statistics. Okay. The converse is also true. And in fact, last time we summarized there are actually 4 equivalent characterizations of sufficiency. One characterization that's particularly useful or intuitive, in my opinion, is the first. It says, if you have the sufficient statistics, of a sample, but not the detail of the sample, right? So going back to the likelihood example, sorry, not the likelihood, but the normal likelihood example. So let's assume you already know X bar, but not the details of these numbers. Okay, can we imagine that situation? It's very common in, for example, academic papers. So you see a statistical report or some sort. It only reports the sample mean and sample variance, for example. Now, you don't know the detail of the data point. It's not in the paper. Now you have to go to the author's website and look at the data yourself. Okay, in the paper only given the mean. Okay, but however, if you assume the model is normal. If you assume the model is location normal, then knowing the sample mean is enough. You don't need the detail. You don't need the detail of the data point. So basically, that's the first characterization. Knowing the sufficient statistics, the conditional distribution of the sample is independent of theta. So this is a very intuitive characterization. Okay, because of this characterization, knowing the detail of the sample do you no good, will not improve your knowledge, because the distribution is simply independent of theta. Actually, we have a very good example last time on the binomial model, which is particularly instructive, taken from Casella and Berger, of course. So imagine you have a sample x1 all the way to xn, and each xi is IID Bernoulli. It's an IID Bernoulli sample. We toss the coin n times, and the sample is the sequence of outcomes. Okay, and the unknown is the probability of xi equals 1, the Bernoulli parameter. Okay, and by the factorization theorem, you can easily check the sum of xi. The sum of xi is sufficient. So namely, the number of head you get in this whole coin tossing sequence. The t is sum of xi, the number of ones in the sample. That's it. And here's the verification. Here the verification says, suppose t is given. Suppose t is given, conditioning on the t is given, the conditional distribution of the sample has nothing to do with it anymore. And indeed it is. And indeed it is. So the joint distribution of the sample The joint PMF of the sample given big T is equal to a constant that independent of theta, 1 over n choose T, 1 over n choose T. And let's think about what this means. This is very intuitive as well. So here you have n slots to fill up, 0 or 1. Right? By filling up these slots, you get the full sample. Here, big T equals little t is given. So that means the number of ones is fixed. So you just need to select. You just need to select t, little t of slots and fill them with 1, and the rest must be 0. And that decides the sample. So what the result says is, of course, you have n choose t possible samples, and they're all equally likely. It's nothing to do with theta. So knowing t is enough. Right? Knowing little t is knowing the total number of ones is enough. And knowing at which position one occurs is not useful. Right? So that's the notion of sufficient statistics. Sufficient statistics is the ancestor of modern dimensionality reduction. All right, so I think that's a very comprehensive recap of what we did in a few streams back. All right, so let's just get started with the new material now. Okay, on the minimal sufficient statistics. Here we go. Yeah, minimal sufficient statistics. Given that a sufficient statistics makes a reduction in the data without losing relevant information in the data for inferences about theta, we look for sufficient statistics that makes the greatest reduction. Because right? We've been talking about existence of sufficient statistics. We didn't talk about uniqueness, right? We never guarantee uniqueness. In fact, sufficient statistics aren't unique. So here we're interested in a sufficient statistics that makes the greatest reduction. All right, so such a statistics is called a minimal sufficient statistics. Minimal sufficient statistics. Definition 6.1.2, a sufficient statistic big T for a model is called a minimal sufficient statistics whenever the value of TS, T of S, can be calculated once we know the likelihood function. Okay, let's think about this definition for a moment. T is called minimal sufficient, okay? And suppose T is sufficient. It is called minimal if it is determined by the likelihood. Oh, and why is that? Why does that make the greatest reduction though? Because the intuition is we wish to find a sufficient statistics among all possible sufficient statistics that makes quote-unquote the greatest reduction. Of course, this isn't clear. Right? What is the greatest reduction? Well, here, this definition says, okay, so even though it's not clear to me why this gives the greatest reduction, but let's just keep going. So mathematically, this is not hard to understand, right? If you know the likelihood, if it is determined, then it is unique, right? I mean, it's still not unique. It's still not unique because, I mean, you can have one-to-one correspondence. Like in the location normal model, you can pick the sum of xi to be sufficient, which is true, and you can pick x bar to be sufficient statistic, which is also true. Of course, I mean, they are equivalent, right? There is a one-to-one correspondence between them. You will never have uniqueness. Right? You will never have uniqueness, but in a sense, this is a class Right? The looking for a sufficient statistic that makes the greatest reduction. This is still a class of sufficient statistic, not necessarily just one. Okay, but let's just keep reading the comment here. So a relevant likelihood function can always be obtained from the value from any sufficient statistic. Right, so yeah, this is true. Yeah, this is true because that's in the definition of sufficiency. Right. The whole notion of sufficiency is if you have identical sufficient statistic values, then the likelihood are equivalent. Right. So if you know the sufficient statistic, the likelihood function can be obtained. Just to relate, likelihood is not probability. No, not at all. We spend a lot of time on this. We spend quite a lot of time on why likelihood isn't probability. So likelihood is just a ranking system. Its absolute values are meaningless. It's just a ranking system on the parameter space, on this set of values of possible parameters. It is sort of like I made that analogy. It is sort of like the utility function in economics. It doesn't really exist, but it gives you the preferability of consumer bundles, consumer good bundles. Right. Here, the likelihood function just tells you the relative value of the likelihood function tells you which values of the parameter are more preferable, in the sense that it explains the sample better. Square free, I'm not sure what that means, but yeah, here, let's keep reading the sentence. So a relevant likelihood function can always be obtained from the value of any sufficient statistics t, but if t is minimal sufficiency as well, then we can also obtain the t from any likelihood function. So you got this relationship. So t always decides L. But if the opposite is also true, then we call t is minimal. All right. It can be shown that, if a minimal sufficient statistic gives the greatest reduction in the data, in a sense, okay, here it comes. If t is minimal sufficient and u is sufficient, then there is a function h such that t equals u hu. Okay, cool. I mean, we can live with that. So that's the result, but it needs to be shown. Okay, you know what, guys? I have my trusted Casella and Berger on my side. I will just briefly glimpse through it and see if I can find such a proof, such a proposition. Now, this is a key. This sentence explains the terminology. Why it's called minimal. If t is minimal, okay, and it's a sufficient statistics, and then any other sufficient statistic u can be expressed as, hold on a second, why is t as a function of u, not a function? T as a function of u that's a reduction. Because h is not necessarily injective, right? Then there is a function hu equals t. So by applying a function to u, you always have the possibility of collapsing information in u. Make sense? It's like, imagine here, h of x equals x squared. Right? This function is not injective. So h of x squared hides the sign of the input x. Knowing the value of h of x, you cannot possibly know the sign of x. So applying a function, an arbitrary function, okay, general function to u, hides it reduces the information further. So in this sense, that T is gives the greatest reduction. Okay, so it's now intuitive. Let's take a look. I will take a look. You can. I'll not show this because I don't want the channel to be demonetized. But you can search Burger online, and it should be readily available. And you can do the same search as I'm doing right now. Okay. So just go to Burger. I'm just literally flipping the page in my hand right now. Chapter 6, Principle of Data Reduction, Minimal Sufficiency. Now, actually, there is a section, 6.2.2. It's been a long time since I read it again. So let's see. That's page 279. So, yeah, I'll just put it in my notes here. What we're doing now. Definition, minimal sufficiency. This is also covered in page 279, Burger. Now we'll probably take a look at the treatment by Burger as well. Here, let me just write down the definition of minimal sufficiency given in Burger. Actually, that's page 280. Burger says, a sufficient statistic big T of X is called a minimal sufficient statistics. Actually, that's the definition here. A sufficient statistic T of X is called minimal sufficient statistic if for any other sufficient statistic T prime of X, Tx is a function, which is literally this sentence here, equivalent, is a function of T prime. Okay, so of course this is, I mean, there are different definitions, right? So we need to reconcile the two. Okay, let me just put down the minimal sufficiency as defined in Evans and Rosenthal here above as well. A sufficient statistic, big T, is minimal sufficient, is a minimal sufficient statistic if the value of, if T of S is determined by the likelihood. Okay, so you have um, supposedly two equivalent definitions. We need to reconcile the two. So remarks. One says because um, L is always decided by T. Minimal sufficiency is also divided by L. Any sufficient statistic, T determines L. But for a minimal sufficiency, the opposite is also true. Should be more precise and say the value the value of the value of T of S can be decided by the likelihood function. The functional form may still not be decided, right? Because as we mentioned, the likelihood function for the location normal model, if is known, if that is known, then X bar is known. Then X bar is known, but we still don't know the choice of T, right? The choice of T can be, say, X bar, or it can be the sum of Xi, right? So I'm just saying there's distinction between the two. The likelihood function is a function. If that is fixed, then you know the value of T of S, provided you're also given the formula for T of S. Okay, so the value of, okay, so that's a pretty neat description. Of course, it remains to reconcile the two. Hi. Okay, the second says, it justifies the terminology. It says T gives the greatest reduction. Second says T gives the greatest reduction. Or should say the quote-unquote greatest reduction. If you don't understand something, raise it. Okay, if you don't understand something, let's say if the definitions still don't make sense, it's okay because we haven't even showed 1 and 2 are equivalent. Okay, it's not you're dumb. I didn't initially get this definition either, and I'm still, I still haven't tried to prove the 2 are equivalent. So it's nobody's fault. Okay? And that's okay. Greatest reduction. So say T gives the greatest reduction of data. This makes sense because by applying a function, you always hide certain information. By applying a function, the function value always will always reduces certain information. The idea is a function, a general function, always always compresses the information contained in the input. Okay, so that's the notion of minimal sufficiency. And um, is there? Well, let's look at some examples, okay, before we attempt to show the equivalence between the two descriptions. Coming back to the location normal model again, by the factorization, we see immediately from discussion earlier, x bar is sufficient. Now, any likelihood function of this model is a positive multiple of this, which we also went over that. Okay, and notice that for any such function of theta is completely specified by the point where it takes its maximum. Exactly. You see, this function is maximized at x bar. At x bar. So if you know the function, you know x bar. You know its maximum point. You know its x bar. And x bar is exactly the minimal sufficient statistics. So here, this is a useful criteria because you can see if the likelihood function is known, x bar must be known. The likelihood function, this is L of theta given xi's and whatnot, right? So, and xi is also s. So that's the likelihood function. If you know the likelihood function, then you know its maximizer, which is just the sufficient statistics. Okay, so you first show this is sufficient, and then this argument shows that it's minimal sufficient. Okay, cool. Location scale normal model. Location scale normal. So this is interesting because here you have two unknowns now. Location scale normal model. So that's the full normal model. You have a sample x1 all the way to xn with that follows ID. Okay, ID follows the ID normal mu sigma square distribution. Mu is in R1. Okay, so mu is unknown. Sigma greater than 0 is also unknown. Both mu and sigma are unknown. Okay, and you just do the same business. You can the algebra is the same. The algebra is the same as in the location scale model. So, but here, theta is a pair. Theta is a pair. So remember we said about the three factors. So they're all essential now. The first term depends on sigma, part of the parameter. The second term depends on x bar, mu, and sigma. The third part depends on the sigma square and sigma and s, the sample variance. Okay, so here you see immediately from the factorization theorem, x bar s squared is sufficient statistic. Why is that? Recall the factorization theorem. The factorization theorem says L theta given s equals h of s. Okay, h of s. This part purely depends on s, and then times g theta of t of s. Okay, we didn't say t is scalar. Okay, t can be vector valued or can be tuple valued. That's fine. So how does the factorization theorem apply here? Well, this is just a giant g theta of t of s. This is just a giant g function, and h is treated as constant here, with h treated as a constant 1. Okay. There's no factor that solely depends on, this is confusing. Here, S is a sample variance, okay? You know what? I should use the Casella-Berger notation, use big X. Big X. Big X is the sample, okay? Big X. So the H is just 1. H is just 1. And this whole thing depends on parameters theta. Remember, parameter theta has two components now, mu and sigma square. And on the sample as well. But it depends on the sample only through two functions, x bar and s squared. So that's factorization theorem. Okay, so let me just quote Casella-Berger again. Okay, I'm just quote Casella-Berger. If you have that, if you have Casella-Berger in some form, okay, then we will then go to page 279. Same example, for which Casella-Berger says, this example demonstrates that for the normal model, the common practice of summarizing a data set by reporting only the sample mean and sample variance is justified. Because the sample mean and sample variance here, you can see, is jointly sufficient. They together form a sufficient statistic, a vector valued sufficient statistic for the location scale normal model. Right. And Casella-Berger continues, the sufficient statistics x bar and s squared here contains all the information about mu and sigma squared that is available in the sample. The experimenter should remember, however, that the definition of a sufficient statistic is model dependent, of course. Right? Sufficient statistics is always implicit. Right? It's always implicit in saying sufficient in what or sufficient for what. Right? As far as the parameter is concerned, a statistic is sufficient. But by saying that, you're already assuming a parametric model. Right? So therefore, sufficient statistic is a model-dependent notion. For another model, that is another family of densities, the sample mean and sample variance may not be sufficient statistic for the population mean and variance. Right? The experimenter who calculates only x bar and s squared totally ignores the rest of the data. They'll be placed strong faith in the normal model assumption. Okay, this is very, very nice idea. Okay, so let me just give you a personal experience, okay, a mentoring experience. So a junior data analyst once came to me and showed me his plot, okay, he showed me his plot, so like the EDA plot, exploration data analysis, okay, and in one example, in one of the, I'm just going to abstract the problem. So in one set of plots, okay, in one set of plots, he aimed to analyze a bunch of binary data, So if you have it, so basically it's the same as x1, x2, all the way to xn, and each of them are in 0 and 1. Okay, so he ran the usual procedure, for in data analytics, and plotted the histogram, the box plot, okay, and a bunch of fancy stuff, just for binary data. I was telling him, so and he also calculated the mean, variance, and various percentiles, like the median, right? Median and various percentiles, 25%, 75%, and whatnot. So the report on that particular set of values takes up pretty much the whole page. So I was asking him, like, do you think it's necessary to do that? Let's say if you already know the mean. Let's say if you already know the mean, do you think it's already do you think it's necessary to do the rest of the things? Let's say the reported mean is 60, is 0.6, because it's an average of a bunch of zeros and ones. So let's say the mean is 0.6. Do we need things like the median? You don't, because this is sufficient statistics. This is a 0.6 is a sufficient statistic, and you don't need the median because you know exactly 60% of these values, x1 all the way to xn, is 0.1. So if you know that, then the empirical CDF is determined. The empirical CDF for this sample is determined. It jumps from 0 to 0.6. At where? Empirical CDF. Because it can only take two values. Right? It can only take two values, so I'm just trying to draw the empirical CDF here. CDF always between 0 and 1. At 1, of course, it jumps to 1. So at 0, it jumps from 0 to 0.6. Okay, so it's like if you reorder the data in an ascending manner, the first 60% of the points are all 0. The rest are all 1. The rest 40% are 1. So you already know the median. Median is a 50% quantile. It has to be 0. So if you know the mean, the empirical CDF is determined, then the median is determined. And in fact, all the percentile is determined. Right? So, and also, what's the variance? Well, the sample variance is what? The sample variance is S squared is 1 over m minus 1, sum of xi minus x bar squared, 1 over m, but you can rewrite this as m minus 1 sum of xi squared, I from 1 to n, minus n x bar squared. But because of these xi's are all binary valued, then you have the sum here, the sum of xi squared. Xi squared is the same as xi. So you see, sum of xi is just nx bar. So that's n over m minus 1, x bar 1 minus x bar. So if you know the mean is 0.6, then the variance is also determined. You see, this is interesting, right? Is it the usual reporting in EDA is redundant? So the guy applied the usual procedure for EDA, did all those plots and sample statistics and whatnot. I would just say, okay, you just need the mean. Because if you know the mean, everything else is decided. Right? So that's a nice application of this idea of sufficient statistic. Okay? But here, let me come back to the location scale model. Here we identify that x bar and s squared is sufficient for this model. Okay, now fixing sigma square. Now fixing sigma square, any positive multiple Possible multiple of L is maximized as a function of mu at x bar. Yeah, exactly. If you fix sigma squared, it reduces to the location model. And only the mu is to be estimated. Then, of course, it does not matter what sigma is. For any sigma, the function as a function of mu, the function L as a function of mu, right, exactly count. Right, this is a count example. You just count the number of ones. That's enough. Right. So, yeah. Here we have in this situation, for every fixed sigma square, the likelihood function as a function of mu is maximized at x bar. This is independent of sigma square. Fixing mu at x bar, then we have this function. Then you can maximize that, I suppose. And you can maximize that. Yeah, so apply the usual procedure in calculus. You first take the log and then maximize. By the way, you treat sigma squared as a single variable. Okay. You're not just differentiating with respect to sigma. You differentiate with respect to sigma squared. Okay, and you can do that, and we will do that in a second. So sigma hat. This is what we call the maximum likelihood estimator. Mu equals x bar, and here sigma hat squared. Okay, sigma hat squared equals n minus 1 over n times s squared is together are the maximum likelihood estimators. This is a one-to-one function of s squared. So if you know the likelihood function of this model, then you can compute s and s bar. So yeah, that's thank you very much, Wendelin. Hi Sunday. I mean, I couldn't hold back to ask you this when you take a break. I would love to how you find such great math books. So this book, of course, it takes I guess it takes experience to compare and select books. But this one, if I haven't mentioned that already, I should mention this every time when I begin the Sunday statistics stream. This is the book by, and it's completely free. So and it has the solution manual. So I guess really, what else? What more could you ask for, right? So Sunday, if you don't know, this is a link of the book. So how do I find a book like this? Well, you spend enough time on the subject, and you're. I mean, I don't claim to be an expert in it, but still, it takes time for you to find a book that clicks with you. Okay. Here, the whole point here, this example shows that it's perhaps our only example so far that we have a higher dimensional sufficient statistic. It's a two-dimensional sufficient statistic. Okay, and it is also minimal sufficient. Okay, so let's move on. If you we also went through the multinomial model last time. So multinomial models are direct generalization of the binomial model. For the binomial model, it models binary data point, binary data. So imagine you now have a ternary data. So each observation can only take three values, three possible values. So I would say binomial distribution are about flipping a coin. Multinomial models are about tossing a die. So here, in one of the previous examples, we showed that you just need the count. So imagine if you toss you just throw is I mean there's no such thing as a three-phase die, but imagine you can do that if you toss a three-phase die n times, and the parameters of interest are the probability for each phase to be observed. Okay, then you just need to count the number of phases in the sequence, number of each phases in the sequence. Okay, Sunday, like you can you can come to the Discord server and ask. A lot of people are very knowledgeable, so they can share their own experience. Let's say just okay, I want to have a good book on subject X. I'm pretty sure somebody will respond in there. Okay, so the likelihood function there. Let's go to example 6.1.5. We also did that a while ago. Here, this is a likelihood function. If you know that, if you know the function, then these exponents can be simply read from the function. Right. So if you know the function, you can read the exponent. So x1, x2, x3 is determined. So, so these are examples we did earlier, and they're all minimal sufficient. Right. All right. So let's now come back to our notes and try to show the result. Now try to show the equivalence between the two descriptions. Okay. Let's try to show the equivalence between the two. We just put it here. Examples. 1, x bar is sufficient for the location normal model. Okay. Sigma naught squared is known. Second, x bar and s squared together is not just sufficient, it's minimal sufficient. Because that's the whole point of this new section. Minimal sufficiency. X bar and s squared together is minimum sufficient for the normal model. So location scale. And 3. So x1, x2, x3 is minimal sufficient for multinomial n, theta 1, theta 2, theta 3. So these are examples. And now we're trying to show 1 and 2 are the same. So I'm going to go back to Casella and Berger and see if there's any results in that section. Actually, after the definition on page 280 in Casella and Berger, it says the following. It says the following. To say that t of x is a function of t prime of x, here, t of x is a function of t prime of x, simply means that, here, if t prime of x equals t prime of y, then t of x equals t of y. Meaning, if t prime of x, for a sample, equals t prime of y for another sample big Y, then t of x equals t of y. So that's what it means. Okay. And remember, sufficient statistics introduces a partition on the data space. Sufficient statistics introduces a partition on the data space. So what do we mean by that? Also recall. Partition. Right? Partitions the data space into equivalence classes. For example, the normal model, normal location, location normal model. A mathematical statistic, yeah, there is. There's actually a place for unmathematical statistics. There is, if you there is actually there is, if you guys know a person called Tuckey, John Tuckey. John Tuckey is famous for, well, many things, one of which is inventing or rediscovering the fast Fourier transform, one of the most influential algorithms of all time. So Tuckey, John Tuckey, he was, so to say, he wanted to emphasize the importance of exploratory data analysis, and he wanted to make the point that all these fancy models don't always tell you the best, give you the best information, because typically speaking, I mean, I'm included, we mathematically inclined people have this tendency of using fancy models, right? But sometimes that's not actually a great idea. Okay, it's not the fancier the math, the better result you get. Right? This is not necessarily the case. So, so go look it up. Go look up Tuckey and his book, Exploratory Data Analysis. And this is now an industry term, right? Exploratory EDA is an industry term. Exploratory data analysis. There's very little math going on. Very much, you can call that unmathematical statistics. Great book. There's no software in there. Okay, all the ideas are illustrated through pencil and paper examples. 1977. Great book. Okay, and he has a few bunch of books in this idea: visual display of quantitative phenomenon, understanding robust and exploratory data analysis. Lots of things. Tuckey started off as a mathematician. in topology, in fact. So yeah, so he knows his math, but he warns against fancy models. All right, so here we're saying that remember sufficient statistics partition the data space into equivalent classes. Right. So imagine X bar is sufficient. Yes, he made a box plot exactly. Leo lecture. The only way to get the best information is go to that Leo lecture guy's channel. For sure. I give you a shout out, Leo. Yeah. So this is, if you're interested in statistics, go check out Tucky's work on EDA. Often there's a sign of amateurishness to use fancy model anywhere. Usually don't know what they mean. Yeah. Well, let's not comment on that too much. So X bar is sufficient. I was saying, what are the equivalent classes here? So Rn, that's the data space. Each data point is each sample is a data point in Rn. It's an n tuple. And the equivalent classes are hyperspaces, hyperplanes that are orthogonal to the span of one. Span of the vector 1. The vector 1 denotes the vector whose components are all 1. All right, so here you go. So that's the equivalent class. And these are hyperplanes that are parallel. They're all orthogonal to the vector 1. Okay, so that's a equivalent classes. What does minimal sufficient statistic do? The partition associated with minimal sufficient statistic is the coarsest possible partition because it achieves the greatest data reduction. It is the coarsest. So basically, equivalent classes is the same as partitioning the data space. You're in a sense you're partitioning the data space into biggest possible blocks possible. Okay, you're using as little equivalent classes as possible, if that makes sense. Here, equivalent classes, for example, of course, there's uncountably many of them, so it does not really make sense from a cardinality standpoint. But you can still think of in terms of coarse or fine. So the intuition is minimum sufficient statistic by achieving the greatest reduction possible in the sense of this definition. If for any other sufficient statistic, T prime, if T prime is known, then T is known. Okay, so the intuition for minimal sufficiency is that the partition associated with minimum sufficient statistics is the quote-unquote coarsest partition. Of the data space. Yeah, so that's the idea of minimum sufficiency. And we wish to show one and two are equivalent. So one gives an efficient way to decide minimum sufficiency. Right? You see, the three examples are all readily recognizable from the first definition. Well, whereas the second is perhaps more intuitive. Okay, so let me just put that down here. Remarks for one. One is more useful for identifying minimal sufficient statistic. Okay, and the second is perhaps more intuitive. Perhaps more intuitive in the sense of explaining so-called quote-unquote greatest reduction of data. Okay, and here's the result in Casella and Berger. Casella and Berger is very candid because this is a definition on page 280. Casella and Berger are very candid. Says using this definition to find minimal sufficient statistic is impractical. Right? So, fortunately, the following result gives an easier way to find minimal sufficient statistics. Okay, so continue. This is the theorem in CNB, page 281. And see what this says. Okay. It says, let f of x given theta be the PMF or PDF of a sample. Suppose there exists a function t of x okay, such that for every two sample points, little x and little y, any pair of sample. Hi, Christian. What's the definition of statistic you're using here? There are a few. So, Leo, there's a few equivalent definitions for sufficient statistics, which we demonstrated their equivalency last time. There are two, but there are four equivalent characterizations. But in terms of definition, we use the following two. The first one says, if T is sufficient, if T of S1 equals T of S2, then the likelihood induced by S1 and S2 are equivalent. So if you have two samples that have the same sufficient statistic, if you have T is sufficient, if you have two samples that gives you the same T value, then the likelihood functions induced by the two samples are equivalent. Knowing the value of the sufficient statistic is enough to get the likelihood function. Okay, and there's a second equivalent definition here. The second equivalent definition says T is sufficient if and only if the conditional distribution of the sample given T does not depend on theta. And here's another characterization of sufficiency. So once again, the idea is knowing T is enough. If you know T, then the details in the sample will not give you any more information about theta. Okay, and the other characterizations has to do with factorizations. Okay, so we will we'll skip those. Okay, so here, let's continue this statement. So on Kellenberger page 281, I strongly recommend you you look it up and open the text yourself. Okay. So the theorem says this is theorem, by the way, 2.2.13. To 6.2.13 in the text, by the way. It says this: suppose you have the density or the PMF, and there exists a function big T such that for every pair of sample points, many pairs of sample points x and y, the ratio f of x given theta over f of y given theta does not depend on theta, if and only if, actually, you know what? We put it here. If and only if big T of x equals big T of y. Then T is minimal sufficient. Okay. So once again, let's take a look at a quick example before we look at the proof. So location model. So for the location model for normal distribution and theta sigma square. Okay, say you have L of f of x. Here x obviously means a vector, big X. Okay, just say f of x1 all the way to xn. Okay, this way there's no confusion. Over f of y1 all the way to yn. Once again, given theta. So this is 2 pi sigma squared, sigma naught squared, to the minus 2n minus half n. I'm not sure if I understand the minimum sufficiency definition. Leo. So this is the idea. T of x is called minimal sufficiency. Is called a minimum sufficient statistic if, first of all, it is a sufficient statistic, and for any other sufficient statistic T prime, T of x is a function of T prime. T of x is a function of T prime. So the idea is if you apply a function to a variable, right, if you apply a function to something, then the outcome hides certain information, can hide certain information, unless the function is injective, right? Then you can always go back to your original input. But generally speaking, a function hides certain aspect of the certain information in the input. That's the idea. A general function always compresses the information contained in the input. Right. So the idea is T of x is the result of the result of compression of some sort of some other sufficient statistic. Yeah, so that's the idea. So that's the intuition. Okay, and the first definition given in Evans and Rosenthal says a minimum sufficient statistic is a sufficient statistic that is always determined, that can be always determined by the likelihood function itself. Right? Remember earlier we said that if you know the sufficient statistic, any sufficient statistic, you always know the likelihood. And for minimum sufficiency, the opposite direction is also true. Leo says, but if I have a sufficient statistic for x parameterized by theta, then for any distribution of what Markov chain? Markov chain is a specific kind of model, right? Markov chain is a specific kind of model for modeling a dependent observation. So you're saying like theta in your Markov chain scenario is the transition matrix, for example. The parameter you wish to estimate is the transition matrix. In that scenario, I think you can, of course, depend on the structure of the I think, yeah, for Markov chain, you can, I've never done actual research on that, but for Markov chain, it is possible to get a sufficient statistic for the transition matrix. I remember from MIT OCW information theory, but I can't link the YouTube stream. Send it to the Discord, and I'll check it out. Okay, so basically here we're not doing anything fancy there, right? It's just the idea that there are two ideas that can equally characterize minimal sufficiency. In general, a sufficient statistic always determines the likelihood. But for minimum sufficiency, likelihood also determines the minimum sufficient statistics. Okay, cool. Okay, awesome. Thank you very much. I'll put it down. 6. Okay, I'll make a note here. Check 4.11 info theory. Actually, we're having an info theory stream next week. I'm very new to the subject. Okay, because I always wanted to learn it, but I just didn't have the time and whatnot to actually look into it. So somebody requested information theory on the stream last week. So we'll take a look at that. Okay. Definition of Markov chain in general is just that I theta t. What? Oh, you're using the information notation, huh? I stands for information, right? I like these notes a lot. Yeah, actually, I have to look into that because it's very likely that there's an information theoretic definition for sufficiency, right? Yeah, so I have to check into that. So thank you very much, because I always know that information theory is linked to statistical inference, and that's actually one of the main reason actually I'm interested in the theory, but I never got the chance to actually take a deep look. Okay, so here you have exponential of minus x bar minus theta squared over 2 sigma naught squared, exponential of, if I recall correctly, what's the last term? Okay. Thank you very much, Leo, for pointing out the resource, as usual. So minus m minus 1 over 2 sigma squared over, okay, got it. Okay, so let's call it sx squared. Okay. And downstairs is pretty much the same form. Okay, information theory makes a lot of stat stuff easier. Okay, I'm very much looking forward to that. Yeah. Because information theory is related to so many things, right? Information theory is, I still don't get the Markov chain thing, right? I mean, it seems like overkill here, but we'll take a look at that. Sure. I'm sorry, Leo. Okay, I'm still not there yet. Okay. So yeah, here we have this ratio. Here has this ratio. So if you know the sufficient statistics are the same. So suppose here you have x bar equals y bar, because for the location normal model, the sample mean is sufficient. Actually, Leo, you got it in the opposite. You said to be minimal, any other sufficient statistic is a deterministic function of the minimum one. It's actually the opposite. Minimal sufficient statistic can be written as a function of any other. Okay, it's the other way around. Here, any other sufficient statistic T prime okay, T, the minimum sufficient statistic, is a function of some other sufficient statistic. It's not okay. I think I know where the confusion arises. It's like you're saying, it's like I think you're trying to say, oh, if T is sufficient, right, then any other sufficient statistic can be derived from it. It doesn't actually work that way, though. It doesn't actually work that way. It's any other sufficient statistic may still a sufficient. Let's say, okay, let's just give a silly example. So here, for the location normal model, x bar is sufficient. For the location scale normal model, x bar s squared is sufficient. So even in the location normal model, x bar s squared is still sufficient. It's still sufficient, but you cannot determine x bar and s squared from x bar alone. You just have the first coordinate. However, the opposite is true. Right? For the location normal model, x bar s squared is still sufficient. It's still sufficient, but you can still there's still room for reduction, right? You can get rid of the s squared. So in the first model, the mu is a variable, so the mu is unknown. Okay. In the second version, mu and sigma are both unknown. So you get that. It's impossible to get s squared simply from x bar. The pair x bar s squared is still sufficient for the location normal model, but you can compress even further. That's the goal. Okay. All right. So yeah, we actually have a nice geometric interpretation of this. We actually have a nice geometric interpretation for 1 and 2. Remember, going back, we draw the picture. If you just look at the 2D model, okay. If you just have a sample of size 2, x1, x2, x1, x2. So the joint distribution is a bivariate normal. The joint distribution S, x1, x2 follows a bivariate normal distribution, right? Spherical normal distribution. Here, only the mean is unknown. So the mean vector lies on the span of 1 somewhere. And what does x bar do? X bar is equivalent to orthogonal projection onto span of 1. So you see, only this subset, the span of 1, is relevant to the inference of theta. So the orthogonal component is a multiple of the sample variance. It does nothing. It does nothing. So you can get rid of that information. For this model, you can get rid of that information here. What's going on? Yeah. So, sorry. Yeah, for this model, you can get rid of the orthogonal component. This is an arbitrary point, x1, x2. That's an observed sample. Calculating the mean is equivalent of orthogonal projection onto span of 1. And where does the mean lie? Well, it's just a span of 1. You don't need the orthogonal component. So that's why for this model, for the first model, x bar is minimal sufficient. X bar s squared is still sufficient, but it's not minimal sufficient. Okay, I hope that clarifies things a little bit. Okay, so now in this example, let's just try to illustrate the theorem in Xellenberger. So if you have x bar equals y bar, then, well, the first two term cancels. The first term always cancels. Now the second term also cancels. So now it is independent of theta. Yes, of course. Sufficiency is always, in fact, statistics is a deterministic function of the sample alone. That's the definition of a statistic. A statistic is a function that depends on the sample alone. Okay, and yeah, so there's that. The idea is if you observe the sample, you can always calculate the value. There's no randomization. Okay, a statistic, it can be an estimator, it can be a test statistic like t-test statistic. In this one, they allow statistics to be randomized. Yes. So if you consider the data points as random variables, then you wish to calculate the distribution of statistics. Then you would consider randomization. Okay, but now we're not even doing that yet. Okay, we're not even talking about the so-called issue, the issue called the sampling distribution. Sampling distribution is exactly what I just mentioned, the distribution of statistics. Okay, but here we're not even there yet. Suppose x bar equals y bar, then the left-hand side equals the ratio of the last two exponential. As you can see, it's independent of theta. So you can see that's the exponential of minus n minus 1 over 2 sigma naught squared, sx squared minus sy squared, independent of theta. Okay, so that's illustration of the result. And of course, the other way is also true. The other way is also true. So yeah, if let's say the middle term can be canceled, that must mean x bar equals y bar. Hang on. Is also true. Okay, so that's the result. And once again, before we look at the proof, can we say something like this? Can we say something like this? So before we look at the proof, can we use the result to show the two are equivalent? Just curious, dude. Working? No, I'm not a quant. Okay. So yeah, Leo, you have a lot to contribute in the next stream on information theory. Okay. So thank you very much. Yeah, I still don't get the Markov chain. This is highly non-trivial, no? Because at no point we mentioned Markov chain. What is the okay? So once again, I might be just talking nonsense here because I didn't even have time to look at the lecture you mentioned. Okay, so Leo was talking about MIT OCW, uh, MIT OpenCourseWare, information theory, 6 for 1 lecture 3. I'll make sure I do that homework before I start the next stream, and perhaps talk a little bit of my own understanding about this issue. All right. So, yeah, here we have these two definitions. Can we use the theorem in Casillan-Berger? Okay, let's not worry about the proof yet. Can we use this theorem to show that 1 and 2 are equivalent? And for that matter, let's just copy the whole thing. 1 and 2. Okay, we'll try. If not, we will look at the proof of the Casillan-Berger in Casillan-Berger, and we will do another example. And after we'll come back. Okay. I know definition of Markov chain. I guess is standard. Yeah. Okay. Is probability of is that a stochastic process? ABC. Is it like a ABCs are Leo ABC that you wrote in chat? Are they are these sequential observations in a stochastic process? Okay. Yeah, I certainly do realize it's like if A means the future. Oh, okay. A goes to B goes to C, or it's the other way around, huh? A should be the okay. I don't understand the arrow notation, but in probability in stochastic process, what you wrote means A is the future, B is the present, and C is the past. So the future is only influenced by the present and not the past. Right? So that is to say the future and the past are conditionally independent given the present. But if you have 3 random variables, you literally can tell the direction of time. Okay, very cool. Just to let's concentrate. Okay, let's concentrate. So here, let's see if the theorem above can show the equivalence of the two definitions. Okay, so well, let's say if we try to use the definition, if we try to use the theorem, it is for proving something is sufficient. It is proving that something is sufficient. So is minimal sufficient. Is minimal sufficient. So how can we do that? Let's say if I want to prove from 1 to 2, how can we, if TFS is determined by L of S, is determined by L of S, TS is determined by L of S. Huh. How do you even express that though? T of S is determined by L of S. It's determined by L. I guess you can say if L given S1 equals L given S2, then T of S1 equals T of S2, determined by the likelihood, right? So let me just put that down here. Determine, meaning L S1 equals L S2, L given S2, implies T of S1 equals T of S2. Also, what is the likelihood? The likelihood function is numerically equal to the joint density. Okay, so yeah, recall L theta given S is defined as f of f subscript. This is a notation in Rosenthal, Evans and Rosenthal. If it's in Cassel-Berger, it would be written in the next way. So is equivalent to f of S given theta. The numerical value of the likelihood function is equal to the joint density or the joint PMF, but the perspective is switched. Theta is a variable. S is considered just joint density exactly. No, not the joint density. Okay, the joint. So like theta is not a random variable. That is, let's look overly complicated. What do you mean by overly complicated? We're trying to show the two definitions are equivalent. That's the thing. That's the goal here. We'll try to show the two definitions equivalent. Okay, so how do you go from 1 to 2? So Leo, just saying here, we don't consider theta to be a random variable. Okay, theta is just a parameter that parameterizes the distribution. Yeah. So, okay, coming back to the two definitions, how do we show they're equivalent? So, I mean, we can at least attempt to start proof 1. Yesterday, I believe at the start of the stream, somebody asked me, okay, how do you do proofs? There's a certain format you can follow to get you set up in the right direction, simply from the structure of the statement. So, assuming 1, proof 2, what do? Well, assume. Okay, assume L given S1 equals L given S2. Implies T of S1 equals T of S2. This is the same as saying the value of T of S is determined by L, by the likelihood function. Okay, and what we need to show is we need to show yes to Leo's last question. Probability for the discrete case, probability density for the continuous case. Need to show the second. I need to show the second, that is to say, for any other sufficient statistic T prime, okay, need to show for any sufficient statistic T prime, T prime of S1 equals T prime of S2 implies T of S1 equals T of S2. And this is trivial. This is completely trivial because by the definition of sufficiency, T prime is sufficient. Then T prime of S1 equals T prime of S2 gives you the same likelihood. gives you equivalent likelihood. Not the same. Actually, they give you equivalent, but not the same. Actually, is this too much? It's determined by you don't need them to be identical. You don't need them to be identical. It's determined by the likelihood function. You is equivalence. Equivalent likelihood is enough. I mean, here the sentence says if the values of TS is determined by L of S. Let's go to the example and check again. Do we need exact same likelihood? We don't need that, no. You see here in the location normal model, for sample with the same X bar, their likelihood may not still be exactly the same. They don't have to be exactly the same because the likelihood we derive there, you see, only the middle part that has theta dependency has X bar in it. So the idea is if you have two samples with the same X bar, the last factor can still differ, but the likelihood functions are equivalent. You don't need literally equal, but just equivalent. That's okay. So equivalence likelihood means one likelihood is a multiple of another. C of S1, S2. Okay, so assuming the first likelihood is a scalar multiple of the other likelihood, then T1 equals T of S1 equals T of S2. So that's assuming one. That's assuming one. If you have equivalent likelihood functions, then the value of the minimum sufficient statistic must be the same. Okay, and this is trivial because this just follows from the definition of sufficiency. Okay, let T prime be sufficient, be a sufficient statistic. By definition, by this definition here, by this definition, since T is sufficient, whenever T of S1 equals T of S2, the likelihood are equivalent. And then it implies the minimum sufficient statistic are the same. So you're done. By definition 6.1.1. So, the 1 to 2 is trivial. So how about we do 2 to 1? How about we do 2 to 1? So suppose we have the second. So for any other sufficient statistic T prime, T is a function of T prime. T is a function of T prime. So we then try to show given equivalent likelihood, the value of big T is determined. Okay, so assume T of X has the property that T of X has the property that for any sufficient statistic t prime of x, there exists a function h such that t equals h of t prime. Okay, assume 2 and wish to prove 1. Need to show equivalent likelihood implies need to show or say t is determined, the value of t of s is determined by L of s, L given s. So that's what we're trying to show here. Okay. All right, so that's the 2 to 1. Can we show that? T is determined by L of s. You know, why don't we start with arbitrary t prime? Why don't we start with arbitrary sufficient statistic t prime? Let t prime be a sufficient statistic. Okay. Then given the value of, damn, my screen went black. Okay, so given the value of t prime, we need to show that t of s is determined by t of s. Okay, gotta head out. Okay, thank you, Leo. Thank you very much for joining the stream. So we want to show that let s be, I guess, let s be fixed. Huh. Sorry. Here the t has this property. T has this t be a sufficient statistic. Then use the assumption. By the assumption, t of s equals h of t prime of s. Hang on a second. Do we need to use this result here? The result says, in Casella-Berger says, so if we can, the result in Casella-Berger, then T is minimum sufficiency. So in the minimum sufficiency here is defined in terms of the Casella-Berger definition. But here we are assuming the Casella-Berger definition want to show 1. So this result would not help us here. Actually, it will not help us. This would not help us because we're now assuming the conclusion. How do we get from 2 to 1? Assuming t prime to be sufficient, then t is a function of t prime. Okay. We need to show the value of t is determined by L. Here, t, we know it can be determined from any sufficient statistic. Can we at least derive one sufficient statistic from L, though? Well, I guess so. You can use the factorization. So why don't we just do that? why don't we just do that? So L, assuming there is a probably. Hold on a second. Do we assume the existence of a sufficient statistic actually? 2 says a sufficient statistic T is called a minimal sufficient statistic if for any other sufficient statistic. Okay. So we want to prove for all sufficient statistic T prime. Okay, sorry. We want to prove that. I mean, I'm confusing myself here. So let's just go back to what I wrote. Assume T of x has the property that for any sufficient statistic T prime, there exists a function h such that T equals h of T prime. That is, we're assuming 2. We want to show that T is determined by L. Okay, we should show that no, T is determined by L. Oh, actually here, we need to add an extra assumption that T is already sufficient. Yeah, because that's in the definition as well. A sufficient statistic T has this property. Let's assume Tx is sufficient. Assuming T is sufficient, then we can write the L in as a factorization. So yeah, that's the factorization theorem. By factorization theorem, since T is sufficient, L of theta given S is equals H of S times G theta of T of X for some function H and G. I am not quite sure. I'm not quite sure. So assuming you have the factorization, I was hoping to get a function. You see, I was hoping to get a function of another sufficient statistic. But I can't seem to use that. Can't seem to use that. So, and this factorization usually isn't unique either, because you can choose what constant to be observed and decide what H and G. So H and G are not unique. The factorization theorem does not guarantee uniqueness in H and G. Okay, so here this is odd. What we can do if the values of T of S is determined by L of S. Here, why don't we go to the previous formulation? Need to show if L given S1 is a multiple of L given S2, you have T of S1 equals S2. How about that? So we need this, right? So we basically we need from this assumption there exists a function. We don't know what this function is. Damn. Hmm. That is very odd. Okay, so guys, I think I might need to AI this. I might need to AI this and see what ChatGPT has to say. Okay, because I'm confused here. So, okay, let me just say, there are two definitions of the minimum sufficiency. I wanted to show their equivalence. Okay, definition one. Um, a sufficient statistic uh, T is a minimal. That's okay. That's totally okay. The point of this stream is to suffer. Okay, um, is to find out where things we don't understand. Okay, I mean it. I think it's more perhaps more fruitful than doing the exercises, quote unquote, the exercises. You can you can probably crunch out the results by applying the mechanical process, but we're trying to understand things. Have you tried co-mathematical? I have no idea. Okay, I have no idea. What is co-mathematical? I have no idea. Equivariance. Equivariance, that's a separate principle. If you look, I assume you're talking about the equivariance principle in Cassel and Berger. It's a totally different story. It's not relevant here. Okay, so I just try to show the equivalence. Definition one: a sufficient statistic T is a minimal sufficient. Is minimal. The point of the stream is not to do some mechanical exercise and feel good about ourselves. Because this is not what I plan to do. My I am purposefully trying to find places I don't fully understand. Okay, this is a minimally sufficient statistic if the value of T of S is determined by L of S by the likelihood function. Again. Okay, that's the definition one. Definition two, a sufficient statistic T is called minimal sufficient statistics minimal sufficient statistic if for all for any other I think by the way, just a brief comment, I think Leo and I think on very different wavelengths. I'm not sure if you guys can tell. By the interaction with me and Leo, we think in very different wavelengths. So I'm more of an analyst and applied mathematician, if I can call myself that. Okay, but Leo is more algebraic and computer science focused. So we tend to think on different wavelengths. So sometimes I can't understand what he's talking about, but I mean, of course, he did give me the reference, so I need to check that out. Right. So he approached the subject of the topic of sufficient statistics from an information theory point of view. Yeah. So if any other sufficient statistic t prime, t is a function of t prime. Okay, so let's see what ChatGPT says. The key ingredient is factorization. Oh, I feel that factorization should play a role somehow. All right, go ahead. So here, let scripted x a. Hold on a second. What is this? Okay, let's just consider this. Okay, p theta in big theta to be a statistical model, and big T from big X. Big X is sample space, the data space. Okay, to be sufficient. Definition 1, likelihood characterization. T is minimal sufficient if the likelihood functions are proportional. Yeah. If the likelihood function is proportional, independent of theta. Okay, equivalent, right? Just equivalent. So we figured this part out. Yeah, this is order theoretic characterization. I think this is what Leo was talking about. T is minimal sufficient if for every sufficient statistic t prime, there exists a measurable function g such that t equals g of t prime. We ignore issues of measurability in this series. Okay, so in other words, every sufficient statistic contains at least as much information as t. Okay, definition 1 implies 2. One implies 2 since okay, hang on a second. Suppose definition 1 hold. Okay, we want to show okay, t equals g of t prime for some g. Suppose t prime to be sufficient. Suppose definition, okay, suppose we have the likelihood characterization. Then you have factorization. Okay, now you suppose t prime of x equals t prime of y. Okay, so the b factor is the same. So x will have a proportional likelihood. Apply definition 1. If you have proportional likelihood, then t is the same. The definition 2 holds. Every level set of t prime is contained inside the level set of t. So here we have proportional likelihood by definition 1. You should have same t. You should have same t value. So starting from the fact that starting from that t prime, so starting from the fact that t prime of x equals t prime of y, you have deduced t of x equals t of y. Right. So basically, this part is done. This part is done. Okay, so 1 implies 2 is done. Did we manage to do that as well? Although it looks a little bit different because we didn't use factorization. Somehow I did not use factorization. Because I already I used the definition in 6.1.1. Okay, in there we said if sufficient statistics have the same value, then likelihood is automatically proportional, and then apply definition 1, you're done. Okay, this is by assumption. Okay, so essentially we bypass factorization because it's already baked into the definition 6.1.1. Okay, so that's cool. What about the other direction? Definition 2 implies 1. Now assume definition 2. Suppose you have proportional likelihood. We wish to prove t equals t2. Assume definition 2, okay? Assume definition 2. Did we do that? I think we did. Assume definition 2, right? Assuming t is a sufficient statistic and has the property that for any sufficient statistic t prime, there exists h so that t equals h of t prime. Okay, assume definition 2. And we need to show the value of t is determined by L. Perhaps we were a little bit vague here. We should perhaps say this. So we should assume proportional likelihood. And we wish to, yeah, so basically we wish to show this. We need to show this. Okay, let me just, I should have used the assumption here. Because this goal is not easy to work with. Okay, need to show proportional likelihood implies identical values in the big T. Okay, so let's go and here see what it says. Defines the equivalence relation. Okay. Oh wow. Yeah. Well, we've been talking about equivalence relation the whole time, but we never bothered to give it a notation. Define the equivalence relation. Okay. Define the two samples are equivalent if their likelihood is proportional. And now you have equivalent class. Cool. We claim that R is sufficient. What the hell? What do we want to prove? This is a choose one representative from each equivalent class. Okay, this involves axiom of choice. Okay, choose one representative from each equivalent class for any x in big C. For any x in big C. Remember what equivalent class is about. So this is the equivalent class of the data space. This is equivalent. I mean, AI might be talking nonsense. Let's be always mindful of that. Okay, so here you have factorization. Why do you have factorization? What is XC? The hell is XC? What the hell is XC? So, I'm construct likelihood equivalence statistics. What is XC? Because it's not defined. Let's press that. What is XC? Oh, it said let XC to be the each equivalence class from C for any x in big C in the equivalence class. For any x in C. Yes, this is true. The joint densities are proportional. Yeah. Yeah. This is true. What is R? What is R? Denotes the statistic that records the likelihood equivalence class of the observation. More precisely, define the equivalence relation. Yeah, this is what we saw earlier. For each sample point, let X bracket to be the set of points Y such that Y and X are equivalent. So this is Rx is simply the equivalence class X belongs to. Okay, so now you have, so the notation, isn't there an abuse of notation? Isn't there? Oh, wow. This is a sufficient statistic that is a set valued. This is set valued. There's nothing stop us from doing so. There's nothing stop us from doing so. So here, R of x is um, R of x is a set. H of R. Well, this is very smart. This is a very smart idea, because what I struggled with here, remember, here what I struggled with is I struggled to use this assumption. I struggled to use assumption. Remember, I said, oh, for any sufficient statistic t prime, where do I cook up this t prime? Hi Thomas, where on earth do I cook up this t prime? This is very smart because we can simply take the sufficient statistic to be the equivalence class. To be the equivalence class. This is a set valued function. It picks the equivalence class. So it says, yeah, I was saying for general sample space, choosing one representative from every may require the axiom of choice. Yeah, so I was saying that does it need axiom of choice? But you know what? Let's just assume axiom of choice is okay. We didn't do measurability either, right? We didn't do measurability, so we're not. This is not completely rigorous, but I think we found the main bottleneck. Right? We found the main bottleneck. So I was trying to prove 2 to 1, right? two from 1. So I was struggling to find this for any sufficient statistic, because in order to cook up this t equals to h of t prime business, you need a sufficient statistic. But what would that be? Well, you can just pick the equivalence class. So that's very, very smart. Okay, so yeah, factorization theorem does not help here. But this is very cool. This is very, very cool. You see? Yeah. Yesterday, somebody asked me, do I use AI? Well, I think the answer ask for yourself. I guess, I mean, it doesn't matter what tool you use. The most important part is to be honest with yourself. Like, I mean, I attributed my failure on doing the proof from 2 to 1 on this specific point. I couldn't use the assumption because I don't know what sufficient statistic t prime to pick. Right. Okay. So once you have that, then well, then you're done. Okay. So okay. All right. So let's write this up. So define equivalence relation. S1 equivalent to S2. Two samples are equivalent if their likelihood is proportional. So, and now define the equivalence class. S bracket to be S prime such that S is equivalent to S prime. This is equivalence class. Okay, and then we define R. We define R. Define R as R of X, R of S as equivalence class of X. So this is a statistic. This is a statistic. It is unusual, right? It is unusual because the value of it is a set, is equivalent class, i.e. R is a statistic whose value is the equivalence class. Where S is in. Like here, we draw this picture. For example, in the location normal model. So if you observe a point in Rn, the R function picks that plane, picks the hyperplane that contains the point, which is orthogonal to the span of 1. But this is of course doable. In the R2 case, it will be like this. So in the R2 case, if the point is observed, you simply draw a perpendicular line. So that's the value. So that's the value of R. I never thought about that. So yeah, so that's basically R. Okay, so this is X, this is S, and this is RS. For example, in the normal theta sigma square model. So this is how R is defined. Okay, so excellent. So this is an example. Okay, so now we have these definitions. We claim that R is sufficient. We claim R is sufficient. So to do that, we can use factorization theorem. Okay, indeed, from each equivalence class C, pick XC in big C as a representative, right? Just uses axiom of choice. Okay, and so by definition of our equivalence class, for every x in C, for every x in C, f, let's use L. Okay, L of theta given x is a constant which depends on x and xc. The whole point is it doesn't depend on theta times the likelihood for xc. Okay, so now you have that. So you can write this part as right L theta given xc . hang on. F, this is, hang on, this is you can write as f of theta xc, f of x xc, xc, okay, let's write h theta of r of x equals L xc. Yeah, because this is a well-defined notion. This is what, because R is the equivalence class. In the same equivalence class, the likelihood are equivalent. So the point is L of theta given x is C, which has nothing to do with theta, times h theta of R of x. Okay, let me just comment. This is well defined. Actually, this is not a great idea. Let me just put it here. C. C is an equivalence class. H of h theta of C. Now, this is well defined since all x prime in all points, okay, all samples in C gives equivalent likelihood. Okay, so therefore we can write the last point here as R of x. Okay. The last factor as h theta of R of x. Okay, and then by factorization theorem, R is sufficient. Sorry, I haven't been looking at chat so far. I'm just trying to finish the proof. R is sufficient. I'll come back to chat really real quickly. And now you can apply the definition. Since R is sufficient, so T is determined by R. By assumption, T equals G of H of R. T is H of R. So what's the conclusion here? We wanted to show if you have proportional likelihoods, then T is the same. Yeah, proportional likelihood here just means equivalent. And they're equivalent, so they're in the same equivalence class. And this is done. So, so this is done. We are done. Since proportional likelihood implies same equivalence class, so same R. T is determined. Okay, so there is that. Okay, all right. Okay, so I think we're happy now. I think we're happy now. So why don't we do one exercise and I'll move on to the ballistic part of the stream. Okay. Can we get a question on minimal sufficiency? Problems. What's the difference here? This is exercises, and here we have problems. Huh. Okay, why don't we try this one? Okay, I'm just randomly picking one. Determine the form of minimal sufficient statistic for the sample size n from uniform theta 1 to theta 2, where theta 1 is less than theta 2. Okay, so I'm looking at this question here. Let's try to apply our knowledge and do this exercise. Actually, because I might have to come back to minimal sufficiency next time because we didn't prove the this theorem. We didn't prove this. Okay, we'll come back to that. Okay. Anyway, let's just do the exercise because we have other stuff to do. Determine the form of minimal sufficient statistic for sample size n in a uniform model. Okay, so let's, as usual, start with the likelihood. Let x1 all the way to xn, ID, uniform, theta 1, theta 2. So it just means that, okay, every point is in the interval, theta 1 to theta 2. I don't know if it should be open or closed interval, actually. Perhaps we should use open interval. Perhaps we should use closed interval, but that's okay. No, that's okay. So how do we derive a minimal sufficient statistic for those two? For theta 1 and theta 2. You have two parameters now. Right? So you should write theta equals theta 1, theta 2. Now, this is kind of annoying because this is ordered pair, okay? This is not an open interval. Exercises are for practicing something specific. Okay. Requires some thinking. I didn't know there's a difference. I always thought exercise left as left for the reader are pretty much the same. Okay. Now this is a problem, by the way. This is a problem. So perhaps this is harder, quote unquote. I don't know. It really depends. You should discriminate. Okay, I don't. It matters very little to me. I saw they're just different, like authors uses different terms for no reason, like personal preference. Okay. Anyway, so here, if it doesn't matter if it's an exercise or problem, if it's something that you can't solve, then you treat it equally seriously. Doesn't matter what it's called. So here we have the setup. Let's write down the likelihood. Okay. The likelihood is as follows. L theta 1, theta 2, given x1 all the way to xn. Well, is the product of f theta xi. And what is f theta of xi? Well, f theta of xi of x, okay, is equals 1 over theta 2 minus theta 1. Now, if x is in the interval and 0 otherwise. So you can combine those two as using an indicator notation. So this is 1 over theta 2 minus theta 1. times the indicator of xi belongs to theta 1, theta 2, closed interval. Yes, time to use indicator, exactly. If we want to write things in a compact manner. Well, so the first one is and actually window. I'm making a video. I'm making a video on random sampling, simple random sampling. I'm going to derive some of the results in simple random sampling. That's a topic in sampling survey, and it heavily uses indicator random variables or indicator functions to bypass tedious combinatorics. Sampling. Okay. I think you'll enjoy that. Coming hopefully tomorrow. I've been saying that. Sorry guys. So theta 2 minus theta 1 to the minus n. And the indicator product has a nice feature to it, because the indicator equals 1 if and only if the set or the event is true, right? So if you have a product of indicator, that just means you get an indicator that is associated with a joint event. So all of them, for all I, xi needs to be in this interval. Okay. So far, I haven't heard any complaint about the handwriting. I assume everybody can find it legible. Okay. If not, I'll slow down. Okay. So there's that. This is the likelihood function. It's a likelihood function, but can we consider it factorizable? Well, the whole thing is just g theta of t. Actually, you know what? Let's rewrite that as follows. I'm going to use the notation of order statistic. Okay, where x superscript, actually it should be a subscript or superscript. What's the, I forgot the notation for order statistic. Perhaps it's down here. Okay, x1. x1, this is the minimum. This is the minimum of all the xi's. And x with a subscript parentheses n is the maximum of all the xi's. So this is order statistics notation. It takes less writing compared to min or max. Okay, so here the indicator can be in the event for the indicator, we can write that equivalently as saying the minimum is at least theta 1 and the maximum is at least theta 2. x1 is greater or equal to theta 1 and xn is less than or equal to theta 2. And the intermediate values don't matter here. And that's exactly our factorization. We're just going to call this our G. Okay? We're just going to call this our H of x1 all the way to xn, which is identically 1 times our g theta t of x1 all the way to xn. So factorize. So this whole thing is g. This whole thing is g. So because you can see it depends on the theta and it depends on the sample as well. Where and t, okay, t of x1 xn is defined as simply two values, x minimum and maximum. This is minimum and maximum. So therefore, this shows that t is sufficient due to factorization. This kind of makes sense because in a uniform model, theta 1 and theta 2 are the theoretical minimum and maximum. And the sample minimum and maximum is sufficient. So there's that. And now we need to show minimum sufficiency. Why don't we consider the graph of L? Why don't we consider the graph of L? So given, say, given T is minimal sufficient, claim, okay, claim T is minimal sufficient. Indeed, how do you recover x1? How do you recover x1? Well, you see, theta 1, let's think about the support of L. The support of L is what? The support of L is as follows. So L is a function of theta 1, theta 2. So let's draw the picture here. So in general, theta 1 and theta 2 has no restriction. Actually, there is one restriction. Theta 1 needs to be less than theta 2. So if we draw two axes, theta 1 is less than theta 2. That means is only under the diagonal. Theta 1 needs to be less than theta 2. So it's like x less than y. Y actually is the upper half. Theta 1 needs to be less than theta 2. So it's the upper half. Okay, let me fill that. So that's the theoretical range. Theoretical, that's the domain of L. That's just the domain. What I'm talking about is the support of L. The support of L. The support means the set theta 1, theta 2 such that, actually, you know what? The support, the support is simply L does not equal 0. That's the support. L of theta 1, theta 2, not 0. So that's the definition of support. So how can that happen? No? Well, the indicator needs to be 1. Otherwise, it's 0. So, theta 2, the theta 2 is greater or equal to xn, and theta 1 is less than or equal to x1. technically the closure of that. Oh, you need the closure? Oh, actually, you know what? Sorry, let me Google that. Support of. Yeah, I guess because you often hear the phrase compact support, like in functional analysis and distribution theory, right? Compact support. Actually, you know what? Here, it doesn't say the closure. This has to be the close, okay? I mean, if you use closure or close support, you see there's a different definition, no? It's not important here, okay? It's not important. What we really care about is the boundary. Yeah, it doesn't matter here. It doesn't matter here. So I'm just saying, like I try to draw the support on the diagram here. So x1 is always greater than x1. X1 is always greater than x1. Actually, x1 xn. Let's think about the point here. X1 xn, x1 order statistic, xn order statistic together is in this set, is in here. So yeah, let me point out. So if a sample is observed, then you can draw a point somewhere in this set, x1 xn. It has to be in here because x1 is always less than or equal to xn. Technically, it might be on the boundary, but let's ignore that technicality here. So yeah, that's the point. That's the point. So in order for L to be in order for L to be L to be positive or non-zero, in order for L to be x, theta 1 needs to be less than or equal to x1. So the x coordinate, the horizontal coordinate, it has to be to the left of this set. Actually here. And theta 2 has to be, yeah, theta 2 has to be greater than xn. Like this, right? So that's the support. So if you know L, you know the L support, then you can read. Then you can read the corner. The corner is the sufficient statistic. So therefore you have sufficiency. The minimal sufficiency, that's what I mean. Make sense? The support is just, as we can see, is the Cartesian product of minus infinity of x1 times xn to positive infinity. You see, because theta 1 needs to be less than x1, theta 2 needs to be greater than xn. So by reading the corner of the support, you get the value of big T. The value of big T is the corner of the support. So it is determined and hence determined by L. And so we're done here. Minimum sufficiency. Show. Okay. Okay. So that's about the statistics part of this stream. And now let's continue to rigid body motion, exterior ballistics, and more specifically rigid body motion. So in the let me just I mean I'm going to we're not going to read much about the book of the book read much of the book McShane and Kelly today, but I just wanted to show what we're trying to do. So because in the last time we've seen two fundamental results for rigid body motions. Okay, and I'm not quite satisfied with the proof, even though I'm pretty sure they're correct, but I just wanted to make them more linear algebraic because this is really a beautiful result in linear algebra. Here, I think is 25, page 25. Yeah, almost there. So, okay, there's a fundamental result here. Actually, two. Every motion of a rigid body can be regarded as the sum of a translation and rotation about arbitrarily selected point attached to the body. Okay, so yeah, I'm trying to show this here. I'm trying to show this using linear algebra. And the second one is the existence of angular velocity. It says this. Also uniqueness. Uniqueness is very easy. Mostly it's about existence. Let B be a body, be a rigid body, and you have an arbitrary coordinate system. Then at each time there is a vector omega called the angular velocity of the body B with respect to the coordinate system, such that the position vectors, so basically that's the relative. The difference is a relative distance, right? The relative distance between 2 points. Relative displacement, not distance. Distance is a scalar. So you have this relation x dot equals omega times x. Equals omega times x. So that's the notion. That's the two relation, right? We wanted to show that. Even though here you have a proof, which I think is I mean, of course, it is correct, but I would rather prefer, okay, it uses more linear algebra. Okay, and the first proof is purely verbal. Okay, so I wanted to recast these two results using linear algebra. So yeah, let's do that. Let's do that. So first we need to give a definition of rigid motion. Okay, so I written some notes yesterday, and I wanted just to have hang on, I just yeah, I wrote some notes yesterday, and I'm just going to show you guys that, which I think is pretty cool. Rigid motion. Because eventually we wanted to get to the so-called 6 DOF. I get the really complex to be used for these theorems too. Well, in 3D, it's not a great application for a complex variable. You see? Yes, I mean you can use quaternion if you if you know in quaternions describe 3D rotation. Okay, but a linear algebra should suffice. Okay, it's not the unique formulation. In fact, there are many equivalent ways to parameterize rotation. Quaternion, exactly, Christian, you're completely correct. So I just wanted to keep the main motivation clear. I wanted to get to exterior ballistics, the 6 DOF, the so-called 6 degrees of freedom, algorithm or model, 6DOF models. Okay, so something like this. Okay, um, so yeah, something like this. So we wanted to model. Um, so here you have, yeah. So you wanted to model the projectile as a rigid body, and as the projectile moves across downrange, there's going to be motions that deviates from the path. Okay, some sort of precession, like a spinning top, like a spinning top. So to model this, you have to use a rigid body formulation. Okay, yeah, something like this. Okay, you can't just treat. The point is, you cannot just treat the projectile as a single particle. Okay. Um, Actually, there's a lesson here. Interesting. I might need to check that out. So basically, this is what we're trying to get to. So right now, we're in the fundamental part, discussing the dynamics of rigid body. Yeah, it'd just be weird in 3D. Actually, you know what? Let me just show you a cool picture. Cool picture. I mean, I cannot show you the full book, but I can at least show you a screenshot of it. All right. Okay, I can't show the full book because of copyright issues, but I'm going to show like a screenshot of it. 6 Degrees of Freedom. And the book I'm showing now is called Exterior Ballistics by McCoy. McCoy is the modern equivalent. I mean, I wouldn't call it equivalent, but more like a successor to McShane and Shelley. McShane and Kelly. Okay. In terms of mathematical rigor, it is not as rigorous, but it covers more modern methods and research. Okay, enough of that. Where's the picture? 6 Degrees of Freedom. I'm still trying to locate the picture. Yeah, so here, okay. So as you can see, the trajectory has an angle, has this angle alpha with uh, with axis, with the axis. So the velocity v, I think this refers to the velocity of the center of mass. See, the v vector and the x vector has an angle. The projectile does not point strictly towards its velocity. Right? The orientation of the projectile is not strictly aligned with the velocity. And the result is sort of a precession. And for that, we have an image as well. So this is what we want to study, and therefore we first wanted to study the kinematics aspect. Yes, right here. The kinematic aspect of rigid body motion, and then introduce dynamics. This is all done by Euler, by the way. I mean, not this, but the fundamentals of rigid body motion is done by Euler. So we wish to analyze this sort of trajectory. I mean, not the trajectory, but the motion here, as you can see, the plane normal to the trajectory. This is the precession. Okay, and both analytically and numerically. So analytically, the idea is, so first of all, okay, the motion it is governed by a linear system, the real McCoy. Yeah. So This is from Modern Exterior Ballistic by McCoy. So 6 DOF model uses rigid body formulation instead of point mass. Okay, 6 DOF, you have 3 degrees of freedom for the center of mass, and you have 6 degrees of freedom for rotation about the center of mass. Formulation. Okay, so this has to do with the stability of projectile. Analytically, we will first going to derive the equation of motion, which in return relies on the kinematics. Dynamics always relies on kinematics. Just pure motion, okay? There's no forces, nothing, pure geometry. Okay, and then you can linearize it. So if you assume that this angle is small, then you can linearize. You can linearize the equation of motion. The equation of motion is nonlinear, and in general, very difficult to solve. There's only a handful, I think 3 cases that has analytic solutions, like so-called closed form solutions, which are also insanely complicated. It requires things like the elliptic functions and hyperelliptic functions. But we're not going to deal with that. We're simply going to linearize it. This is analytically what we can do, and also numerically. And to do that numerically, we're going to introduce, down the road, of course, introduce numerical algorithm for ODEs, okay, numerical ODEs, and in particular, Runge-Kutta. Is it Runge or Rung? I don't know. RK. I always say RK, so I don't know how do you pronounce it in full. Runge-Kutta method, developed from scratch. Okay. Okay. Such as RK45, for example, RK45 is perhaps the most popular ODE solver, save for stiff problems. Okay. So this is what we're trying to do. So right now we're just doing kinematics. Of course, 6 DOF models is typically unnecessary for small arms modeling, like infantry weapons. But this is needed for modern artillery system. 6 DOF models are definitely needed for a modern artillery system, such as the 155 millimeter howitzer, currently used in places like Ukraine. Okay. So we're going to derive the kinematics, and let's start with the definition of rigid motion. Definition. Okay, so we're going to start with a more general setup, and then we're going to specialize things to 3-dimensional space, R3. Okay, simply let V be an inner product space, because the rigid motion makes sense in the general inner product space, a real inner product space. And let a function, okay, a function doesn't have to be linear. A function f from V to V is called a rigid motion if the this stands for the norm. Okay, the norm of fy minus f of x equals the norm of x minus y. So it preserves distance. Isometry, you can call it that. This is an isometry, a rigid motion. So, or isometry. So this is a rigid motion. Of course, if v is just a real line, if v is just a real line, then rigid motion is simply a translation. Remember, in measure theory, one of the properties of the outer measure is translational invariance. Right? It's translational invariance. What we really want is invariance under rigid motion for higher dimensional spaces. Okay, so there's that. Just that, because in 1D the only rigid motion is translation. Okay, so there we go. So and now we wish to define things like oh, actually, I'm going to assume the inner product space is also finite dimensional. I'm not sure if we need that, but I just assume it for the moment. It shouldn't hurt us. Okay, but what we care about really is the finite dimensional case. Okay, we're not doing Hilbert space here. Okay, so now let's define translation and rotation, or orthogonal operator. Okay, orthogonal operator and translation. Definition: a function g, does a reflection also satisfy the equation? Oh yeah. In 1D also there is reflection. There's also reflection. You're right. So it's the yeah, reflection also. What do you mean by reflection though? What do you mean by reflection? So let's say the reflection is minus a. A point, let's say this is a minus a. This is also equivalent to a translation in 1D. Right, so it doesn't really matter. Okay, so here, a function g from v to v is a translation if there exists a vector v naught in v such that g of x can be written as the following. G of x is x plus v naught for every gx, for every x. This should be intuitive. Imagine this is v, and here you have x plus v naught. So this is x plus v naught, and this is 0 plus v naught. This is the translation. Okay, and we also need an orthogonal operator. The notion of orthogonal operator definition. What's the definition of orthogonal operator in inner product spaces? Yeah, orthogonal operator is simply a linear operator that preserves length. Okay. The difference between orthogonal operator and rigid motion is that we don't require in the definition that rigid body is linear. In fact, rigid motion does not have to be linear, right? It's easy to check that the translation is a rigid motion. So definition, let T be a linear operator on V. Okay, if T is orthogonal if T of x length equals x for all x. So it's a linear operator that preserves length. Okay. There you go. So these are three definitions. So now we wanted to show that a rigid motion can be decomposed into a composition of translation and an orthogonal operator. So there you go. Theorem. Let f from V to V be rigid motion. Okay. Then f equals g composite with t for some orthogonal operator t and translation g. Orthogonal operator translation g. So it just means that i.e. f of x equals you first apply t, right? You first apply t, so it's t of x, and then plus v naught for all x. Okay, so that's it. That's basically in the McShane and Kelly, it says it's the sum, right, of a rotation and a translation. So that's the theorem we wish to prove. Okay, just using pure linear algebra. Proof. Let's go. So okay, so how do we define t? Let's first define t. So given assume t is rigid. Okay, assume t is rigid. Assume f is rigid. An obvious way to define t is as follows. That is, t of x is simply f of x minus f of 0. So this way you get rid of the constant. So this is t for all x. Okay. And claim t is orthogonal. Claim t is orthogonal. So how do we do that? Right? Because from that claim, if you show that t is orthogonal, then you're done. Right? Then you're just done. If shown, the theorem follows. As the g of x is simply x plus f0. Right? So that's the claim. You need to prove linearity first. Yeah, t is orthogonal. We do need that. Yeah, we need. Yeah, it is orthogonal operator. By being an operator, it is orthogonal. It assumes it's linear. Christian, very nice. You wanted to show t is linear. Okay, so um, let's consider the following. So t is, first of all, it is rigid, right? So first of all, t is rigid. Actually, you know what? Let's use f is rigid. So first we can notice the following. F of t of x length squared is the, by definition, is the length squared of f of x minus f0 squared. And since f is rigid, is x minus 0 length squared. So it's just x length squared. So showing that it preserves length is not hard, but we need to show linearity. Okay, so therefore t of x length equals t of x equals x length for all x. So t preserves length, i.e. so t preserves length, and now it's just a matter of showing t is linear. Okay. So to do so, let's consider also, we claim that t is preserves inner product. Okay, so it might be a little bit surprising that if t is if t preserves length, then immediately it preserves inner product. Right? The opposite is obviously true. If t preserves inner product, then well, lengths are defined in terms of inner product, then t preserves length. Right? So it turns out that the opposite is also true. If you have t preserves length, then t also preserves inner product. So let's see how that works. So claim, second claim. Actually, you know what? This is not the second. I don't want to do the second claim. So t also preserves inner product. So let's see how that works. Let x and y in V be arbitrary. Let's consider t of x minus t of y square length. And because of the length is defined in the inner product space, you can expand this as follows. So it's t of x length minus 2 times the inner product of t of x times t of y. Is it because of inner products are like a projection of the result? The reason is polarization identity. Okay, the real reason is polarization identity. We're basically trying to show that. So let me just after I finish, I'll show the polarization identity. I'll just write down leave it as an exercise for you to prove. But anyway, so yeah. So you can do this expansion and use the fact that t preserves length. You get x length squared minus 2 times tx ty inner product plus y length squared. Okay? Okay, cool. And because, on the other hand, this is also the same as x minus y length squared. Because tx minus ty is just fx minus fy, which is x minus, which has the same length as x minus y. Why do you need to prove linearity on T? We need to show, because it's not given in the premise, no? We just have F is a rigid motion. We want to show F equals the composition of G and T for some orthogonal operator T and translation G. So here, because in the definition of rigid motion, we do not assume a priori F is linear. In fact, F isn't. So by writing T equals F minus F of x minus F0, we don't know T is linear. To be an orthogonal operator, it first needs to be a linear operator. Orthogonal operator is a linear operator that satisfies this length preserving property. Okay, that's why we need to show T is linear. Okay, we managed to show T preserves length here, and now we need to show T is linear. It didn't say let T be a linear operator in V. We need to show there exists. We assumed F is rigid. That's all we assumed. We want to show there exists T and G, such that T is an orthogonal operator and G is a translation. Right? We define T to be f of x minus f of 0, but this does not immediately lead to that T is linear, no? So basically, that's why we're doing it. Okay, so let me just write that down here. On the other hand, by the fact that T preserves distance, also so you can expand that as well. So it's x length squared minus 2 x and y inner product plus y length squared. So now by comparing these two, comparing 1 and 2, compare 1 and 2, you get T of x and T of y inner product equals the x and y inner product. And this is the same for all pairs of x and y, i.e. T preserves inner product. Okay, and the reason for that is actually, I was saying, it's because of the polarization identity. Now, what's the polarization identity? So in an inner product space, in an inner product space, the inner product can be expressed in terms of norm. Everybody knows the norm is defined by the inner product, but the inner product can also be expressed in terms of norm. Okay? And the reason to and the way you do that is very easy. You simply write x plus y squared equals x, much like what we did here, x length squared plus 2xy inner product plus y inner product, and you just rearrange and you get x and y inner product equals 1/2, okay, x plus y norm squared minus x norm squared minus y norm squared. So therefore, if T preserves the norm, it must preserve the inner product. So there's that. Okay, simple as that. Okay. So T preserves the inner product as well. Okay, and let's continue. Now we need to show that t is linear. Okay, to show t is linear, need to show a linearity. That is t of x plus ay equals t of x plus aty, or all a, or all scalar a. Right. Let me consider the square norm, because we've been working with square norms. So let's consider t of x plus ay minus tx minus aty, square norm. So what do we do? Well, still, let's consider an expansion. Let's consider the first term as a whole, okay? And then you expand. So you get t x plus ay minus t of x length squared, and then minus 2a, you can pull out a because of bilinearity, in a product of t x plus ay minus tx, sorry, ty, and then plus a squared t of y length squared. All right, so there's that. Okay, and now we're going to use the properties of t. So the first term is equals x minus ay minus x. You can get rid of the t, length squared. Okay, that's the first one. You can do the same for the last one. You do the same for the last one, but before that, let's first expand the inner product using bilinearity. So you get 2 minus 2a, inner product of x plus ay ty, okay, plus 2a inner product of tx ty. Okay, that's the expansion. And finally, a squared y norm squared. Okay. And the nice thing is, the first term is simply ay length squared, which cancels out with the last. So this term and the last term cancels. And now we're just left with the two inner product. Oh, actually, no, they don't cancel. They're the same term. They're both plus sign. My bad. So you get 2a squared y norm squared. Yeah. And use the inner product preservation property. So you get 2a. This is just x plus ay and y inner product. The third term is 2a x and y inner product. And you keep expanding. So 2a squared y norm squared minus 2a x and y inner product. You keep expanding, and then minus 2a squared y and y inner product, which is just y length squared. And now you see what happens. Everything cancels. So this is 0. So this is 0. So you see, it is actually implied. It is actually implied if an operator is orthogonal, it must be linear. Right? So yeah, so what we're essentially doing is if an operator is orthogonal, it must be linear. So Christian, you need to prove linearity first. That's indeed correct. But if you actually, you can isolate this, you can isolate this result and simply say a proposition. If T preserves length, if not even assuming linearity, you can, but it fixes the origin, okay? If T fixes the origin, if T of 0 is 0, and T preserves length, then T must be linear. So linearity is implied, actually. So linearity now is shown, so we're done. Okay, so this proves the theorem. Every rigid motion can be decomposed into orthogonal operator and a orthogonal operator and a translation. Okay. So and now we wanted to say something about the orthogonal operators in R3. Okay. Now we wanted to specialize to R3 and describe a rotation. I want to define rotation. Let me just check my notes real quick. Theorem. An orthogonal operator in R3 called R in R3. I want to say something along this way. Okay, so an orthogonal operator, I wanted to show that it has a real eigenvalue. It must have a real eigenvalue, which is 1. It must have one real eigenvalue, 1. Actually, is that true though? Hmm, is that true? Okay, let me think about it. Okay, so first of all, the orthogonal operator. I mean, just leave it this statement now because I'm not quite sure if that's true. But actually, it's not because you also wanted to preserve orientation. Okay, so let's define definition. Define a rotation to be an orthogonal operator that also preserves orientation. definition. And a rotation is an orthogonal rotation in, let's just say R3, okay? From now on, we only care about R3. Is an orthogonal operator R in R3 such that determinant of R is 1. The determinant of R is 1 fixes the orientation. Actually, you just need determinant to be positive to fix the orientation, but because of orthogonality, determinant has to be plus or minus 1. Okay? In general, if R is orthogonal, then you have R transpose R equals I. And as a result, the determinant of you can take determinant on both sides, you get determinant of R squared is 1. So determinant can only be 1 or minus 1. Okay, and we're picking the determinant equals 1 to be the rotation. Okay, this is what we care about. We want to preserve orientation. Okay. Plus or minus 1. That's the general determinant. Okay, and now we wanted to show that 1 is an eigenvalue of R. Proposition. And actually there's a notation for that, right? The notation is R is in SO3, special orthogonal group. SO3. So this is a notation. Rotation is all the rotations is SO3. 1 or minus 1, yes. In general, orthogonal operator has determinant of 1 or minus 1, but a rotation is defined as determinant equals 1. You wanted to preserve orientation. Okay, and that's the definition of SO3. All right. So the proposition I want to show that 1, if R is in SO3, then 1 is an eigenvalue of R. So that's what we want to show. Okay, so let's go ahead and do so. Proof. So suppose you have, let's write down the eigenvalue eigenvector equation and see what that implies. So suppose you have RV equals lambda V, and you're going to take the norm on both sides. So by taking norm on the right side, you get lambda absolute value times V norm. Okay, so on the left, because of R preserves the length, so there you go. You have V norm equals lambda. Yeah, characteristic polynomial has degree 3 and orthogonality. That's pretty much it. Okay, and then you can cancel out V length because eigenvalue is always assumed to be non-zero. Okay, so lambda absolute value is 1. Actually, this should be understood as the complex modulus. Right? This is not absolute value in the real sense. Well, of course, complex modulus subsume the notion of real absolute value. This is complex modulus. Okay, so now we've shown that any eigenvalue must have modulus 1, i.e., okay, any eigenvalue lambda, any eigenvalue lambda must have modulus 1. Modulus 1. And now because of R is 3 by 3, the characteristic polynomial is real coefficient and degree 3, right? So by the fundamental theorem of algebra, it has 3 complex roots. It has 3 complex roots, and because of the real coefficient in the characteristic polynomial, the roots are comes in pairs. So that means if lambda is a root, then lambda bar, the conjugate, is also a root. And you only have 3 roots, so one has to be real. Okay, so let's write it that way. Use the fact that R is real and 3 by 3. Since R is real, the real matrix, real 3 by 3 matrix. Okay, I'm going to use matrix and linear operator synonymously because this is in Rn, doesn't really matter. Okay, the characteristic polynomial of R has real coefficients. Therefore, if e to the I theta, because I'm using the Euler's formula, okay? Any eigenvalue lambda has modulus 1, so you may write lambda equals e to the I theta for some theta, for some real theta. Intermediate value theorem. Yeah, this is dimension 3 magic, exactly. Because of e to the I theta, if e to the I theta is a non-real, e to the I theta is a root, aka eigenvalue, then so is e to the minus the conjugate, e to the minus I theta. Yeah, so it has a real root. So it must have a real root. So therefore the eigenvalues, there are the 3 roots. There are 3 roots of the form e to the I theta, e to the minus I theta, and lambda 3. It's called lambda 3. And the first 2 multiplies to 1. Right? The product of the eigenvalues should be the determinant. Right? The determinant of R, which is 1, should be the product of all the eigenvalues. And therefore lambda 3 is 1, so you're done. Indeed, dimension 3 magic. So what does that mean? Well, there exists an eigenvector, therefore, so this is QED, so therefore there exists a V non-zero such that RV equals V. So this is the axis of rotation. So this proves that for any rotation there is a rotation axis. For any rotation in 3D, there is a rotation axis. Every rotation has a rotation axis. Because RV equals V, R fixes the rotation axis. Okay. And what are the other 2? What about the other 2? Well, the other 2 are exactly the rotation by angle theta. The other two eigenvalues, isn't that beautiful? E to the plus or minus I theta corresponds to rotation in the plane perpendicular to the axis. And why is that rotation axis? Sorry. Actually, rotation about the plane. Rotation. Yeah, e to the I theta. This stands for plane rotation. Right? In the plane perpendicular to v. This might need a proof, but because I'm running out of time, but perhaps it's a good exercise. Okay, I will try to prove it next time. I'll try to prove it next time. So now we have this this full characterization, right? So we have this linear operator. I'm sorry, we have this rigid motion which can be decomposed into orthogonal operator and translation. You can always do that. And in R3, we care about rigid. We care about the we care about rotation. We care about rotation. Yeah, not just any orthogonal operator. We care about rotation. We don't want reflection. Okay, so and next we wanted to get to the notion of angular velocity. Okay, so how can we derive the existence of angular velocity? So now let's consider angular velocity. That is x dot equals omega cross x. Where does that come from? For some vector omega. Okay. Angular velocity omega. So where does that come from? Okay. In mechanics, usually you just draw a picture, okay, and call it a day. Okay, this is omega, the axis. This is x. This is the rotation plane. In most physics books, you just give the picture and call it a day. But what we really care about is why omega is a vector in the first place. Why is omega a vector? Why does such a vector exist? Because having a direction and a quantity does not guarantee a vector. This is something I mentioned that in the post. 3D rotation, as we just shown, has an axis and a notion of angle, and a notion of angle theta. Right? So you can consider theta as the magnitude and v as the direction. So why can't we consider any arbitrary 3D rotation as a vector? Because SO3 is not a vector field. SO3 is a highly nonlinear, it's a manifold. Right? And to put it more concretely, SO3 does not satisfy commutativity. SO3, if it's a vector space, then vector addition should be commutative. Right? It's like translation is commutative, adding vectors is commutative, but adding rotation makes no sense because the order matters. Right? So in general, 3D rotations are not vectors. So why can omega be a vector? This begs the question. Right? So the moral of the story is, in physics, what they usually say is, even though rotations aren't vectors, instantaneous rotations are vectors. So if you imagine, if you just rotate by a very small angle, then the sum of two rotation matrix approximately commute. So this is very interesting. But yeah, this is a pseudo vector. Yeah, this is a pseudo vector because Yeah, this is a pseudo vector. From the point of view of tensor analysis, this is indeed a pseudo vector because it depends on the choice of orientation. Okay. Anyway, so let's derive the existence of omega. Yeah, let's derive the existence of omega. So, in consider you have a differentiable function. Differentiable function RT, which is in SO3. So this is a matrix valued function that is differentiable. That is to say, for every t, the R transpose t times RT equals I, 3 by 3. And the determinant is always 1. So you can imagine this is a rotation whose axis and rotation speed may change over time, but it remains a rotation. Determinant of R equals 1 for all t. Okay, so there's that. So you have, this is a general RT, a general rotation, time-dependent rotation. So for a vector fixed in the body frame, we're using the terminologies from McShane and Kelly. So let's consider the body frame. Let's consider a vector fixed in the body frame. Now, centered at the center of mass, for example, it doesn't really matter at this point. In the body frame, fixed vector, let's say x naught, fixed in the body frame. Its coordinate in the space frame so imagine you can imagine there is a spinning top. Okay, so relative to the body, that point is fixed. Of course, relative to the laboratory frame, it is moving. Okay, the rotation axis is like this, and it precesses along the z-axis, for example. This is a general situation. So its coordinate in the space frame is x of t equals r of t. Right? It's just a rotation function applied to x naught. So now we wish to consider its time derivative. Right? So that's the time evolution, and let's differentiate xt with respect to time. Right? D over dt. D over dt, you get x dot equals r dot times x naught. X naught is constant. Okay. So what can we do here? Well, we can also write x naught as rt times xt, because the inverse of r is simply rt. By orthogonality. And as a result, x dot is r dot times rt times x. Okay, so now you have this relation. Let's define big W to be r dot rt. Define this big W to be. This turns out to be important here. Define big W to be that. And let's think about the implication here. So x dot is big W times x. Therefore, you have this relation. So this is a differential equation satisfied by x. Of course, W is not a constant. Okay, W is R dependent. W is T dependent, of course. Just wanted to confirm that W is T dependent. But let's think about the property of W. Now let's consider d over dt on the relation to the relation, apply d over dt to the relation R transpose R equals I. So we have the orthogonality condition. So what does that give us? Well, you can apply the product rule. The product rule still holds for matrix multiplication, by the way. So you just get R dot T times R plus RT R dot. On the right hand side, obviously get 0 because it's a constant. Okay. So notice something here. So we can, this is awfully similar to W. And we can cook up a W from this expression, from the result of differentiation. And how do we do that? Well, I wanted to, because RT is on the right of W, so I wanted to move this RT to the right. Okay. Let's multiply RT to the right. R dot T R RT equals plus RT R dot RT. Okay, just multiply RT on the right, gives you 0, and this is I, and therefore let me just move it to the left. There's no need to put it here. Let me just say right multiply RT which gives us R dot T plus R transpose R dot RT, yeah, equals 0. And then left multiply R. Yeah, that's the trick. Left multiply R, so on the left you get R dot T, okay, and plus RT R dot RT equals 0. So RT is once again I, therefore R dot T plus R dot RT equals 0. So equals 0. So notice, what is this? This is just W. This is R dot RT. This is W. So it begs the question, what's the left term? What's the left term? Well, the left term, or take transpose of the equation. Indeed, let's consider the W transpose. W transpose, consider the fact that W transpose is R dot RT taking transpose. This is just R dot transpose. R dot transpose and R transpose dot are the same, right? The derivative obviously and transpose commute. So therefore you get W transpose plus W equals 0. So this means W transpose is minus W, i.e. W is antisymmetric or skew symmetric. So W is skew symmetric. And what's so nice about skew symmetric matrix, the 3 by 3 skew symmetric hides a vector. So you can write W as the following. So you can write W as 0 minus omega 3, omega 2, omega 3. The diagonals are obviously all 0. Okay? Minus omega 1, minus omega 2. You might wonder, okay, why on earth would I write this? It's because of the correspondence between skew symmetric matrices and vector cross product. Yeah, so you can always write a skew symmetric matrix this way, which we can always write. You can write it as follows. So x dot equals wt. W is skew symmetric. You can easily verify that x dot equals, I'll close the stream real quick, as omega cross x. As omega cross, where omega is omega 1, omega 2, omega 3. Okay? Just use the definition of cross product and you can verify that it is equivalent to the matrix multiplication Wx. The right hand side is equivalent to big Wx. So that's the angular velocity. So that's the angular velocity. And we're pretty much done. We're pretty much done. You can show that, because I wanted to close the stream real quick. It remains to show that omega is belongs to the eigenspace of 1. Remember here, in a rotation matrix always have 1 as an eigenvalue, and the corresponding eigenspace is the axis of rotation. So I'm trying to say is omega remains to show, that is to show R omega equals omega. R of t, omega t equals omega t. So this way it tells you that this omega lies in the rotation axis. So therefore this diagram that you see in physics class makes sense. Okay, so we're going to call it a day. Thank you very much for joining the stream. I hope you guys found the content interesting, and I'll see you next time.